Let's take a look at another way to integrate or calculate a volume of a solid of revolution. Let's take and revolve the region bounded by. So now, AK, I'm actually going to physically put two curves in here because I'm not going to go around the x-axis. I'm going to go around the y-axis this time, okay? So I want to take two curves, y equal cosine x, y equal minus cosine x. Cosine and sine are both waves, right? Cosine and sine are both waves. Cosine starts high and finishes high on a range from 0 to 2 pi. So let's see if we can't draw these things. Let's take y equals cosine x, y equals negative cosine x. So cosine starts high. At pi over 2, it hits the axis. At pi, it comes down to -1. At 3 pi over 2, it hits the axis again. And at 2 pi, it goes up to 1. So this is what cosine does. Cosine does this. Negative cosine x is simply a reflection in the x-axis. So negative cosine x does the exact opposite. Now we're restricting ourselves between pi over 2 and 3 pi over 2. So I'm going to go ahead and erase some of this stuff here so that it's out of my vision. And I'm going to focus my attention and center my attention on the region bounded by those two curves, y equal cosine x and y equal negative cosine x. Y'all good so far? And then we're going to take and send that shape about the y-axis this time. It is a donut. Hello, it's a donut. Today is National Coffee Day, I learned. It is a donut, right? You send that shape, right? Take that shape around the axis and you get a donut with a hole in it, right? A donut with a hole in it, right? You guys can see our donut sitting there, right? You can see it. So, thus far, we have been doing integration by cutting perpendicular to our axis of rotation. So far, in order to find this volume for this donut, we've taken the donut and we cut perpendicular to its axis of rotation. We slice it right across the middle, okay? We slice it right down the middle, and we get washers. You see what I'm saying? We would slice it this way, horizontal, right? We'd slice it horizontally. Can you picture a knife just slicing it horizontally, right? And you get a washer, and we pull off a washer. So our cross sections so far would have been an integration of washers. We would take pi r squared minus little r squared, and we'd be taking dy. Why is this a bad method to use with this particular set of curves? Can you tell me why that might be a bad method to use? Yeah, Reese.
Because like the cross sections, like even though in terms of dy, they're like flat, like they're stacking this way.
They are, absolutely they are stacking this way. And when we stack them, notice when we stack them, we're cutting this way. And so our inner radius matches our function on our outside. What else were you going to say, Hannah?
Basically, since like the inner radius to the outer radius is using the same equation.
The inner radius to the outer radius is using the same equation, exactly, right? Not only that, but because we're integrating with respect to y, we have to rewrite our functions as x equals something, right? Because we're integrating with respect to y. Are you with me? And when we integrate with respect to y, we have to write our functions in terms of y. So how on earth do you convert? What do we do? It would be an arc, right? An arc cosine. So we would have to take the arc cosine of y to solve for x. And then we'd square an arc cosine. And you integrate a square of an arc cos. Are y'all with me so far? I am not a happy camper, okay? Not only that, but arc cosine is only defined on the interval from negative pi over 2 to plus pi over 2. So we got a lot of issues, okay? So washer method is not a good method for many reasons. So that gives us method. The cool thing about that particular method is in order to achieve that, I will be making cuts. I will put my axis back in there again, right? My axis of rotation. I am cutting circles around that axis of rotation. So what happens is, with the shell method, I am going to cut parallel to my axis of rotation. Watch. We're going to cut parallel to my axis of rotation. Boom. That cut runs parallel. Do you see it? The cut right here. I'm going to need this on a test. I want you to show me where is that cut that you're making for a cylindrical shell. It runs parallel to your axis of rotation. Put that on a little index card if it's not making sense, right? Cuts parallel. Now, do you see that when you send this cut around your axis of rotation, the other one was perpendicular, so when you send it around, it gave you a circle. But when you take this cut parallel and send it around, do you see what it gives you? When you take that cut and send it around, do you see how it gives you this cylinder? Can you picture cutting and making a cylinder? And we are stacking these cylinders. Their heights get smaller, but then they get bigger heights, bigger heights, bigger heights, and then they get small heights again. But I'm taking a cylinder with a little bit of thickness. Are y'all with me? So the cylindrical shell method involves taking cuts with a little bit of thickness. And what we're going to be doing is we're going to integrate the surface area of a cylinder. Okay. So not discs, not washers, but cylinders. Now there's something else that's important. Not only that your cut has to be parallel to your axis of rotation, your first homework problem on this set gives you cuts, and it says, is it a washer method or is it a shell method? Like, you have to decide. If it's parallel to your axis of rotation, it's going to be a cylinder. Okay? So, the other thing to notice is, all right, so normally, if we went around a y-axis, we cut perpendicular, and so we would integrate with respect to that axis. But what happens now is if we go about the y-axis, I'm making my cuts parallel, so what I'm actually doing is I'm actually cutting perpendicular to which axis? My x-axis. Do you see that? I'm cutting and making cylinders, but I'm cutting them along the x-axis. So what that means whenever you employ the shell method is you will integrate with respect to the variable opposite what you're going around. So if you are going about the y-axis, that means you're going to have to integrate with respect to x. And my limits will be x limits. Do you see what I'm saying? So those are the two big things that you want to recognize with the shell method. Number one, your cuts are parallel to your axis of rotation. Secondly, you will be integrating with respect to the variable opposite that which you're going around. Okay? So let's talk about this surface area for a cylinder. Here we have a cylinder. It's an empty cylinder. It's an empty cylinder. It has no volume to it other than the thickness. It's an empty cylinder. I'm going to make a cylinder for us. So picture a Coke can, or I don't know what else. Breadcrumbs come in a big paper cylinder or something, right? We got a cylinder. We're not going to fill it. I don't want to know how much Coke goes in here, how much water, how much of anything goes in here. I want to know, though, what's the surface area? How much area is needed for material with a little bit of thickness to it, but how much area is needed to make the material for this can, this cylinder? To get the surface area, one way to think of it is to cut it, open it up, and lay it flat. That's a good way to think about how much area is needed for that surface. Are you with me? That's just a good way to think of it. Are you with me?
Yeah, I like that.
You like that idea? I like that idea too. So every cylinder can be made into 3D, but to get the area, which we know is two-dimensional measurement, you can open it up and lay it flat. So that gives you a two-dimensional measurement. So really, with cylindrical shells, all we're doing is we are integrating rectangles, okay? So that's the preface for, if you have your notes out and you're looking in your notes and you downloaded your notes, that's the preface for the whole basis for a cylindrical shell. A cylindrical shell is a cylinder with a little bit of thickness. We are looking for its area to add up. The area can be achieved by opening that cylinder up and looking at it flat. Now, that rectangle, do you see what happens though? Now, this note here uses X. I don't like to use X necessarily. I like to use radius and height. So I'm going to put my own picture underneath it. Every cylinder has two measurements that you're going to have a label for, really. Your height, which is how tall that cylinder is. Sorry, guys. I am standing right in the way of I don't like this screen. Anyways, I don't like this classroom. I hate this classroom. But that's okay. That's beside the point. But you guys, it's okay. Here we go. So you see, every cylinder has a height to it. Every cylinder has a height to it. Cylindrical shells. Every cylinder has a height to it. And it also has to it a radius. And the radius is always measured from the axis of rotation, but it also has a height to it. And so if I open it up and lay it flat, I'm looking for the surface area, which is just the area of this, which has a height. But like I did with my cylinder, right? If I open it up, my length is simply, if I think about it, my length is simply the distance around that cylinder. That's my length, right? It's the distance around that circle. And a circumference of a circle measures the distance around a circle, the circumference formula versus area, right? Circumference formula. So that length right there is simply the circumference of a circle. Circumference of a circle is 2 pi r. So a cylinder surface area is really opening up and getting a rectangle that has 2 pi r units this way and h units this way. That's where these formula ideas are coming from to set up our cylindrical shell. I'm just going to put here, you always integrate with respect to the variable opposite the axis of rotation. If you're rotating around a y-axis, then you're going to integrate with respect to x. If you rotate around the x-axis, then you're going to be integrating with respect to y because you're cutting along that axis. All right, are you ready to do the problem then? Are we all set? Any questions? How are we? Everybody see my setup? So my setup, instead of pi r squared or pi r squared minus pi r squared, is 2 pi r h. So you are going to see that I am going to be constantly writing 2 pi r h. I know this formula, they put 2 pi xf of x, but I like to put 2 pi r h, and you're going to see me do that. That's the formula that I'm going to be using in my integrals. All right, so let's go back and go to that example that we started with. And I'm going to start with a clean slate because the other one was all messy. You guys already have this in your notes, so it's already graphed. I think my top curve was cosine x, right? So I think my top curve was y equal cosine x was my one curve, and then y equals negative cosine x was my other curve. Is that right? And brown, are you with me? Or was it flipped? Did I have it flipped the other way? Hang on. No, I have it right. I have it right. Hang on. I have it right. Yep. And I'm going to send this guy around the y-axis. So I'm going to rotate this around the y-axis. And so I'm going to use shells, which I know is a cylinder, but importantly, the cut that I make, and I will require you to show me on your test, the cut that you make is parallel to your axis of rotation, right? So the cut is parallel to the axis of rotation. And then you rotate that cut around. And that's what's giving you your cylinder, right? Okay, so we have a cut parallel to the axis of rotation that gets rotated around. Now I want to label that guy. That cut has a height to it, right? Do you see the height? It has a height to it. And it's got a radius. The radius being measured from my axis of rotation. So I've got a height and I've got a radius. This is where it gets a little confusing from the last method, but we're walking slow. So the first thing is making sure you cut it parallel to your axis of rotation. The second thing that's important is making sure you integrate with respect to the correct variable. So because I'm traveling and rotating around the y-axis and I'm going to use shells, what should I integrate with respect to? X. Okay? So we always integrate with respect to the variable opposite that which I'm going around with shells. So I'm just going to say that's the variable opposite the y-axis. Because I'm rotating around the y-axis, I'm going to do dx. And that also informs my limits along the x. What are my limits along the x then? What do you guys have on your notes? What is this guy? Pi over 2, and this guy? 3 pi over 2. Thank you. So that's pi over 2 to 3 pi over 2. Thank you, Carson. And inside, I have the formula 2 pi RH, because that's the area for each of my cylinders. All righty. 2 pi. H is a little easier to see, so how about we start with H? Actually, let me erase that. What's H? What's H? What's H? Yeah. Yes. What? Say what? Why is it on one side only? Because it's going to rotate. Because I'm doing a cylinder. So it's going to go to the other side. Because I'm going around the y-axis, and I am doing cylinders which operate by going around. But I am looking right now for my height. Can you guys tell me what my height is, Laura?
Would it be like negative cosine x minus cosine x?
You got it. So the height, do you guys see your height right here? This is my height. This is the distance. This distance ranges from this brown curve to this blue curve. So my height is the distance from the top curve to the bottom curve. Now I'm integrating with respect to x, so that's nice that it's written in terms of x. So my top curve is minus cosine x. My bottom curve is positive cosine x, but a difference I have to take top curve minus bottom curve. Y'all with me? And so the height is just minus 2 cosine x. So that's going to be my height. What about my radius? Can you see my radius? Gavin.
Is your radius just x?
It is. It is. And this is the confusing part. If I was to ask you, just looking here, what is my radius for this particular cylinder? What would you do? You would look at where it falls on the x-axis. If I moved my cylinder out to here, that guy would have a radius of pi units, right? So really, my radius is defined by where I make my cut along the x-axis. So, as a calculus student, this is all you're going to remember. Okay, I'm just telling you, this is what you're going to remember. The radius will always be the variable of integration. The radius will always be the variable of integration unless you're going around a different axis than the x-axis or y-axis. Like if you go around the line y equals 5, or if you go around the line x equals negative 10. Then your radius has to change because now you're not going around a specific the axis that your main axes. Are you with me? But for now, if you're going around an x-axis or a y-axis, then your radius will always simply be your variable of integration. So in place of r, you're going to put x, and in place of h, you're going to put minus 2 cosine of x. R and H. And so what is the integral that I have to take? Pi over 2 to 3 pi over 2 of, let me pull out, minus 4 pi x times the cosine of x. Is that what you guys got? Which part? Why is Rx? Because what if I said this? What if I said this, AK? Can you draw me a cylinder that has a radius of pi units? Can you draw me a cylinder of radius of pi units? What would you do? So I want a cylinder of radius pi units. Right here. I want a cylinder of radius pi units going about this axis. So you would go to pi, and you'd make a cut, and then you would go about the y-axis, right? And it would make you a cylinder of radius pi. Where did you go to make that cut? You went to the x value, pi. Your radius matches that. Let's say instead of going around this one, I went around this axis. Now, my radius changes. It's going to be pi plus a little bit, x plus a little bit cooler. Yes, do you see what I'm saying? That's right. All right, guys, how are you integrating this? You guys should have an answer for me. What are we doing here? What's my volume? What's my volume? What's my volume? Pull out my cheat sheet. Integral of x cosine x. Evaluating this. dv is cosine of x dx. So derivative of u is dx. Antiderivative of dv equals antiderivative of cosine is going to be sine. And so it's uv minus the integral of v du. We've got a product, and whenever you got products and integrals that you can't do easily with something else like u sub, you think integration by parts. So let's see what we got going here. So you've got uv x sine x minus the integral of v du sine x dx. Throwing our limits in from pi over 2 to 3 pi over 2. So I got negative 4 pi times, let's see, 3 pi over 2 times the sine of 3 pi over 2. Whoa, Tina, you skipped an integration. Hang on. What's the antiderivative of minus sine x? I forgot to do that. Hang on. That's what? Plus cosine x, because derivative of cosine is minus sine. Yeah, I forgot that little piece right there. My apologies. And you guys are plugging things in, right? Now, Jaden, all you have to know is pi over 2, 3 pi over 2.
That's a lot of pies, like, in a normal circumstance.
It is a lot of pies. But you know what's so cool about pi over 2s and 3 pi over 2s? They just fall at 90 degrees and 270. And so they just fall here on our unit circle at 0, 1, and 0, negative 1. And so the cosine comes first and the sine comes second. So the sine of 3 pi over 2 is just...
You're acting like that made sense. You can put down some numbers on a paper,
Oh,
and then
you ever see the unit circle?
that's foreign to me.
Oh, okay. So
I cheated as much as I could to freak out.
cosines and sines, anyways, they're all based on circular. Sine squared plus cosine squared equals 1. That tattoo is based on the fact that cosine squared plus sine squared equals 1 gives us a fundamental identity. Cosine squared plus sine squared equals 1 gives us a fundamental identity. And if you let cosine be your x coordinate, which it is, and your sine value be your y coordinate, which it is in SOHCAHTOA kind of idea. X is across the bottom of a right triangle, y is across the top, cosine's across the bottom, sine has to deal with the top. Then what happens is every point on this circle, cosine squared plus sine squared equals 1, x squared plus y squared equals 1, every point on that circle of radius 1, if I was to label all my points, have a cosine value and a sine value. Cosine is the first coordinate, the x value. Sine is the second. So when I say 3 pi over 2, I mean 270 degrees. Are you okay with me, kind of?
I get you now.
Pi over 2 is 90 degrees. Are you with me? So help me out here. Now, 270 degrees.
But
What?
I don't have it memorized.
No, look at my circle.
But there's no numbers on
Look
the
at my circle. Where is 270 degrees?
Probably somewhere down there in the lower quadrant.
It is, because 360 goes all the way around, right? So it's this bottom. Right here is 270. Okay, what's my sine?
-1.
It is.
Whoa.
Whoa. Okay, that was easy, huh? What is my cosine?
I mean,
Just look at it.
it'd be flipped, right?
No.
Oh,
Cosine. Thank you. What is the sine of pi over 2?
It's like the half of the one, so it's like something.
90 degrees. Look up at 90 degrees.
It'll be 1. And then 0.
Yes.
Oh my gosh. Math is crazy.
No, math is beautiful. It is beautiful.
I can't believe it sometimes.
You know what's amazing? Is amazing, really, that math was coming from taking and describing the universe into something that makes sense. Well, that's what it's supposed to do. You guys say, nope, not at all. 3 pi over 2, so 3 halves minus 1 half is 2 halves, or just pi. Would you guys all agree? 3 halves minus 1 half is just 1 pi. And so it looks to me like the volume of this shape is going to be 4 pi squared cubic units. Did I mess it?
3 pi minus 3 pi.
2 pi over 2?
Yeah. Or
It absolutely is 2 pi over 2, Laura. Did I mess it? Go ahead, Matt.
You did your sine 3 pi over 2 is negative.
Oh, my bad. Thank you. I lost it. So it's negative 3 pi over 2 minus pi over 2, which actually is minus 4 pi over 2. Thank you. I just messed it all up. Okay, hang on. We got a mess. Okay, hang on. Scratch that. This is negative 4 pi times negative 4 pi over 2, which is negative 2 pi. Sorry, that is 8 pi squared. That's a little bigger than we wanted. Thank you. Cubic units. Thank you guys for catching that mistake. Absolutely. Second example. Alrighty. Use the method of cylindrical shells to find the volume of the napkin ring obtained by rotating the shaded part of the circle x squared plus y squared equals 100 about the y-axis. These are all online if you've downloaded in the notes. Yes, sir.
Oh, so that's
6 to 10, right? That's 6 to 10. Do you see it? So this guy is 6. This is straight from your homework. I copy and pasted a problem straight from your homework.
What's the
Say what?
What's the equation of the thing? That part.
Oh, x squared plus y squared equals 100.
So that's the equation of the circle.
It is.
Yeah,
Or what's the equation of that shaded stuff?
it's still the equation of the circle.
So that is this, right, AK?
No, yeah, that is that.
That is that, right? And what other piece? Oh, what is that equation? X equals 6, right? If it goes up and down, straight vertical line, x equals 6. They put 6 less than or equal to x less than or equal to 10 instead of writing x equals 6. But we're going to do a setup, right? And we are going to rotate about the y-axis, everybody, right? You're going about the y-axis. So on your test, first problem, here you go. Here's a shape. Make the cut, draw the cut that will help us define the cylinder for cylindrical shells. Make a cut that defines a cylinder that we could use for cylindrical shells. Make the cut. Make the cut. I don't have a cut. Where's the cut? I want it right smack in the middle of my area. Have you ever seen me put a cut on the either end? I always cut it smack down the middle. You don't want a napkin ring, huh? You don't want a napkin ring. Well, actually, so I guess I should sketch my picture first, right? I guess we could sketch our picture first. What's happening is we're getting this shape right here, right? Right, you got this, like, you know what I mean? You know what, where you stuff the napkins down and it's fancy around the outside kind of thing. I don't know, there's other things that you could see that shape. Oh, probably like, maybe you're making a well, not really a thermos, because, well, it could be a thermos. It could be a well, maybe, kind of, not quite. Could be a thermos that's kind of circular thermos or something like that. Yeah, yeah.
Check my integral.
Let me see. So what are you integrating with respect to? We're integrating with respect to the variable opposite what we're going around. Close. Close. Very close. Very close.
Would it be negative?
Nope. Very close, though. Very close. So make sure you show me your cylinder, okay? I want to see this. I'm going to require it. One of our problems is going to have you draw the cylinder in, draw a disc in, draw a washer in with the cut. I want the cut. I want the thing that's actually helping to define my shape.
I have a question.
Yes, sir.
I'm a bit confused trying to. Like I have it all graphed up. I'm just a bit confused what you're doing.
Okay, so ready? I'm good. This is what we're going to do, Grant. Step 1 is I'm going to write down my integral symbol, And I'm going to say to myself, because I'm rotating around the y-axis, I need to be integrating with respect to...
What do you rotate? That's one thing.
Oh, what I'm rotating is this. I'm making cylinders. Well, I'm rotating this whole shape, right? Because we're making a solid of revolution. So I'm taking this area here, and I'm rotating it around. And I'm creating this solid of revolution.
But that would just make a ball.
With a hole in the middle, right? With a hole in the
No,
middle.
that would just make a ball.
With a hole in the middle.
Where's the hole? I don't understand.
Well, okay, Grant, if I take this whole thing and rotate it around, then I get a ball, right? But I'm not taking this whole thing. I am taking only a piece of this. So it's like a ball with a cylinder hole down the middle of it, you see?
So we're just rotating the green bit.
We're just rotating the green bit.
You had me confused. You want me to rotate the whole shape?
Sorry, I misspoke if I wanted you to rotate that whole circle. I just wanted you to rotate that green bit. Sorry, my bad. Does that make sense? I mean, do you see it? Do you see it now? I'm sorry about that. Sorry, guys. I got so excited about my cylinders. Do you guys see what we're doing, right? We're taking that green area. We're rotating that green region about the y-axis. And 2 pi, no, slow down, Tina. I know I'm integrating with respect to x because it's the variable opposite that which I'm going around. If I'm going around the y-axis, then that means I have to integrate with respect to x. And I'll just put a little note, opposite of y-axis, because we are doing a rotation around the y-axis, but we're doing shells, so we're going to do dx. And that tells me what is my limits. Chase, did you get limits on that for me? The x limits? Yep, that's exactly what it is. 6 to 10. Good. And in here, we have 2 pi. Well, I just thought I thought he had the answer. That's why I asked him. I figured he'd have the answer. So, hello? What, AK? Oh, slow me down. 2 pi x. When you're doing shells, that radius will always be your variable of integration if you're going around an axis, the y-axis or the beautiful 2 pi x times the height, right? Okay, so let's look at my picture. What is my height? It is the top function minus the bottom function. Oh, there is a root. So what do you do? Oh, so I see what you're doing. Let me see if this is what you're doing real fast, and let me make sure we're on the same wavelength. You took this equation and you solved for y because we're going to integrate with respect to x. So we want to solve for y to get all gobbledygooks in terms of x, right? And so everybody got that y is plus or minus the square root of 100 minus x squared, right? The positive square roots on top, the negative square roots on the bottom. Do you see that? So,
I saw where I did.
good. So the height, did you get this? The root 100 minus x squared minus the bottom, negative 100x squared. So my height is actually 2 square root 100 minus x squared. So I'll just put that in a think bubble. This is just in a think bubble. One on the top, one on the bottom. There you go. 2 of them. I love it. You got 2 of these. Absolutely. So I'm not going to do this one out, but I am going to say what would I do to do this out? What would I do to do this out? Okay. You can just U sub. This guy's a simple U sub. I'm not going to do it out because I want to have time to set up one more. But this one would be a U sub. What would you let U be, everybody? 100 minus x squared. Perfect. Good. And then du, Yusuke, would be negative 2x dx. It would be root u, right? Which then turns into 3/2 with the 2/3 in front. So it would be a u sub, but for sake of time, I'm not going to do it out, okay? My other class, I actually did it out, but not this one. They didn't do the integration by parts one. So, but I know, crazy. I know, isn't that funny? I know. That's okay. I wanted to make sure we got through this. Does anybody have questions on setup before we do one more for practice before we go home for the weekend? We're going to do one more for practice. Any questions on the setup? It's next. It's after break. It's after break.
Okay.
The test is after break. Don't worry. I'm not going to give you a test on Wednesday when we have to learn. We have at least 3 more talk days in class before we do any. Tony, do you want me to go back? Let's go back one more time. Question. Hang on, guys, everybody. I want to hear Tony. Go ahead. The U sub part? You want to write it down? Shall we write it down? Oh, or are you okay with that there?
No, just put it on my paper.
He's okay.
I'm good.
I'm going to just stop for a minute. I'm just going to wait. I should take a bite of my donut, huh? My bad. Are we ready? One more. You guys are just... Are you okay now? Are we good? Is everybody good? Here you guys go. Did we not do an E yesterday? Did we not set up an E to the X yesterday? We did, but we used a disk method or a washer method yesterday with the E to the X. Okay? Today, we want to do it a different way. Oh, wait. Yeah. I'm going to let you guys set this one up for me, okay? You guys set this one up for me. I want the region bounded by y equals, and let's hang on a sec. Don't do this one. Should we go about the x-axis, or do you guys want to do this one about the y-axis again?
I want to see one on the x-axis.
Let's go about the x-axis. I mean x-axis. Let's switch it. Let's switch it up. Sorry, guys. Let's switch it up. The other one will be a good review. When we come in, that'll be our warm-up problem when we come in on Monday, okay? What is that curve? What is that curve?
Wait, are we doing the X?
No, hang on, slow down. I switched our problem. Did you see I switched our problem? Sorry about that.
No, that's okay.
Gavin said, let's do one about the x-axis because he's going to get his homework done this weekend. I'll tell you what, some people have already finished their last homework set. Quite a few, actually. You did quite a few problems on that one. Gavin, you did too, right? I thought you did. Oh, maybe not that one. Okay. It's not due. It is due tonight, isn't it, Chait? I mean, get it done. Carson, get it all done.
Is it not? Oh, it's still. It used to be due tonight.
Yeah, it used to be.
I did. I switched it up. All right, guys, what is y equal to the square root of x minus 1? Help AK out. What's it look like? It's a sideways.
Points connected.
Oh, you got Desmos. Desmos will work too. It's a sideways parabola, right, guys? We got a sideways parabola.
When you do the sideways, I always assume in my mind it always looks like this.
Yes, it
I always
does.
forget that it goes down like this.
You don't want the other half because that's the negative part.
I know, but like last that we agreed the other half.
Because it was written x equals in terms, it was x equals last time.
The other half together.
No, because it's y equals. Do you see the difference, Grant? 5 goes to... So, you guys are getting this. Oh, no, not that one. Undo, Tina. You're getting y equals the square root of x minus 1, which is the square root function shifted over 1 unit. And then y equals the square root of 2. Huh. Well, how do you find out what the x value is? You set your curves equal to each other, right? So you would simply say, when does the square root of x minus 1 equal the square root of 2, square both sides. So what is x? 3. When x is 3, it gives me y to be square root of 2, right? When x is 3, it just gives me y to be square root of 2. Good question. Excellent question. excellent, excellent, excellent question. I want you to answer that question for me.
Oh, wait.
Well, it is in
Well,
the
actually,
direction,
don't leave it on.
but
We're rotating around the
besides.
x-axis. I could use the disk method.
6 roots.
What would be, just make it a little more complicated. What makes it a little more complicated is that part of the shape is solid and part of the shape has a hole in it, do you see? And so you would actually have to split up your integrals because your curves change on the bottom. Do you see what I'm saying? That was your So we could do washer method. We could do disk washer method, but you would have to break it up into one integral here and one integral here. And that's okay. That's perfectly fine.
But if you do center,
Except the directions
would it just be
say
easier?
cylindrical shells.
Well, we're going to do cylindrical shells right now.
But you saw this.
We're going to do cylindrical shells right now. Okay? Now, with cylindrical shells, if you're going around the x-axis, you want to be integrating with shells with respect to y. So, when I go to set up my integral, we are going around the x-axis. So I want to set up my integral, and I want to integrate with respect to y. So that tells me my limits have to be y value limits, which are going to be what? 0 to square root of 2. Thank you, Carson. Awesome. You like this stuff, don't you?
No, I'm just ready to
No, you're doing. Oh, I see. Okay, so let's hurry this up a little bit. Okay, so it's 2 pi RH. All right, here we go. So what is r? R is y because the variable matches the variable of integration because we're going around an axis, x-axis. What is h? Whoa, I didn't put my cut in. Hang on, let me put my cut in. It is important. My cut is parallel to the x-axis, right? My cut is parallel to the x-axis to make my cylinder, right? My cut is parallel to my axis of rotation, so it makes my cylinder. Are you with me? The height of that cylinder. Hello, Carson. What's my height then? You gonna help me out here so we can get out of here, right?
like y squared plus 1 or something?
Well, let's figure it out. Our equation, what is our equation? Y equals, what is my equation? Square root of x minus 1? But I'm integrating with respect to y, so you have to rewrite it in terms of, right? So what do I do to him? Square both sides and add 1?
Isn't that literally?
Oh, did you say that? I didn't hear you. Sorry. So the height is simply y squared plus 1 minus 0, right? Let me write that in there.
Well, I have to.
And then it was a polynomial, right? We would just FOIL it out. I'll put ... because then you would just FOIL it out, right? Y cubed plus y, and then it would be 1/4 y to the 4th plus 1/2 y squared, and then you'd plug things in.
Wait, isn't foil like the?
Not FOIL, distributed out. I used the
Okay,
wrong
I was
word.
like-
Sorry.
I got
Distributed out. Sorry. I didn't mean to confuse you. Absolutely, it's not first out or inner last, unless we put a 0 with the y, but that's okay.
Jaden wants to know
Ask away, Jaden. What's your question?
Oh,
why there's not one on the bottom.
what happened to the 2? Why is there not one on the bottom? I don't know. That question was like.
No, it's not a bad question. Trust me, I had a nice discussion with Milo in the last class for